This is a video for problem 218 in Engineering 623. That problem says, consider the transmission line circuit shown in the accompanying figure. Compute the incident power, the reflected power, and the power transmitted into the infinite 75 ohm line. Show that power conservation is satisfied. So in this case, the first thing we note is that the source impedance is 50 ohms and the characteristic impedance of the first transmission line is 50 ohms. So that means that we can approach this problem in the same way as we did in the easy method of solving 216. Now, and one more thing, this 10 volts in the current problem is a peak voltage rather than RMS value. So when we look at equation 237 now, we do need to have the factor of 1/2 in there. Now here is part of equation 237, the 1/2 Vg over 2 squared times 1 over Z naught. Now remember, in equation 237, this term right here, the 1/2 times Vg over 2 squared times 1 over Z naught, that was multiplied by 1 minus gamma squared. The reason for that is that equation 237 gives us the average power delivered to the load. And the reason for the 1 minus gamma squared is that the 1 represents the incident power, and then the gamma squared represents what's reflected. So if we just want the incident power, which is what this problem first asks for, is the incident power, then we don't multiply by 1 minus gamma squared, we just multiply by 1. So there's no 1 minus gamma squared term here. We're just multiplying by 1 to get the incident power, and then for the reflected power down here, we'll multiply by gamma squared. So everything else here, I believe, is self-explanatory, and so we get 0.25 watts as the incident power, and then for the reflected power, when we use the formula for gamma, Z load minus Z characteristic over Z load plus Z characteristic, we get 0.01 watts. And so if 0.25 watts is what's incident on that second transmission line, and 0.01 watts is what's reflected, then we can conclude right there, if we go ahead and assume that power conservation works, and of course there's no reason to suspect that it would not be, if we assume that power conservation works, then we can immediately conclude then that the transmitted power, the power transmitted into the second transmission line is 0.24 watts, and we're done with this problem, except for one thing. We have not shown that power conservation works, we have merely assumed it. And that's a very quick and easy solution. But if you want to actually show that power conservation is valid here, then you need to use a method that's more similar to our brute force method for solving 2.16. So let's see how that would go. So since the length of the first line is lambda over 2, the input impedance is the same as the load impedance, which is 75 ohms. The load here is that second transmission line, which has a characteristic impedance of 75 ohms. So the input impedance to the first line, since the first line has a length of lambda over 2, that input impedance will be 75 ohms. And so to find the power delivered by the source, now since we know the input impedance is 75 ohms, the source impedance is 50, that source is 10 volts, so the power delivered by the source would be 1/2 times that V squared over Z total, or 1/2 times 10 squared over 50 plus 75. So the total power delivered by the source is 0.4 watts. Now, using a similar analysis, the power dissipated in the 50 ohm source impedance is 1/2, and here's the voltage across that source impedance and divided by the impedance of the source impedance, and we get 0.16 watts. And the power transmitted down the line, same kind of idea, 1/2, and here's the voltage at the input, and divided by the 75, which is, as we said, the input impedance, and we get 0.24 watts. Now, this right here is what we needed. The 0.24 watts is the net power going down the first transmission line, the net power. And so that net power is what goes into the second transmission line. So this proves right here, we have proven what we concluded up here above using power conservation. Up here, we got P transmitted with 0.24 watts by using power conservation, but here we haven't used power conservation at all. We have, now we could have, notice we could have, because we have 0.4 watts is the power delivered by the source, 0.16 watts is what is dissipated in the source impedance. So we could have used power conservation here as well to conclude that the power delivered to the second transmission line is 0.24 watts, but we didn't. We made it a direct calculation to conclude that, but then when we compared what we've done up here above, we see that it agrees, and so that's how we could verify that power conservation is valid. It is working properly in this problem. And so that's it. A rather easy problem 2.18.